All right, so welcome back, guys. Today we're going to be talking about our last section in kinetics here on rate law. So what we're talking about in rate law is basically, can we make a mathematical formula or statement that tells us how fast a reaction happens based on a whole bunch of variables? The temperature of the reaction, the concentration of the reaction, the surface area of the reaction, just a big math statement that'll say, yep, if I know these variables, I can get the answer. So we're going to look at kind of an initial example here. Here's our reaction. Hydrogen peroxide, H2O2, gives me hydrogen gas and oxygen gas. Now there's going to be a bit of background noise because they're doing some construction outside of my door here, as you can probably hear. So hopefully that doesn't get too distracting. If it does, maybe I'll have to redo one of these lessons, but we'll give this a shot and see what happens. So here's the data from the experiment. So here's the deal with the rate law itself. It can only be determined experimentally. There's no real pure, theoretical way to do it. And there's a very good reason for that. It's because it's just too complicated. If you think about it, you would have to have, let's say I was just dissolving salt in water. That reaction rate's dependent on the exact temperature, the exact pressure, the any impurities that might be in the water that you're using if it wasn't exactly purified, the exact surface area of your salt. You'd have to have every salt crystal be the exact same size and shape and surface area to actually have a chance of calculating this. And so they don't even bother with that. We're just going to do an experiment, and we're going to use that experiment to figure out some kind of fudge factor, some number that takes into account temperature and surface area and impurities and all this other stuff. All we're going to really want to worry about are the effects of concentration. So what is the effect of our initial concentration on the rate? And so because when we're starting this experiment, we're starting with reactants, all we care about is hydrogen peroxide, H2O2. So whatever our initial concentration of H2O2 is, we're going to do a trial. So trial 1 here. We start with, let's say, 0.1 molar H2O2, and we would measure the reaction rate in some way. This could be, like if you look here, we're producing hydrogen and oxygen, so you could measure the production of hydrogen or oxygen. So you've got a liquid turning into a gas. You could measure production of gas. You could measure how fast the peroxide, which is the liquid, you could measure how fast the liquid disappears. You could measure pH potentially. There's all kinds of different things you could measure, but they find some way to measure the reaction, the actual rate. So in this case, it's going at 5 molarity per second, 5 moles per liter per second. There we go, that's a little quieter. So cool, 5 moles per liter per second. And we do it again, trial number 2, but we change the concentration. We start at 0.2 molar. And that changes our rate. Now we measure the rate again, and this time the rate's at 10 molarity per second, 10 moles per liter per second. We do trial 3, we crank it up to 0.3 molar, and we're up to 15. Cool. So what do we notice? The rate. What happens when I double the concentration? If I go from 0.10 to 0.20, 0.1 to 0.2. So if I double my concentration, my rate goes from 5 to 10. My rate doubles. Let's use a different color for this one. If I triple my concentration, I go from 5 to... Oh, look at that. I triple it. They're exactly proportional in this case. So our rate is proportional to the concentration of hydrogen peroxide. That little alpha symbol there, that means proportional to. They go up together. If I double one, the other doubles. So in this case, with hydrogen peroxide, it's an exact proportion. We call this first order. It is the rate is going to be equal to the concentration of peroxide to the first power. If I double this, I double that. If this was a second power, for example, that would mean if I doubled my concentration of H2O2, so if I doubled this would go up by 2 squared. Instead of just 2, it would go up by 4 times, 2 squared. So that would be a second order reaction. But this is first order in hydrogen peroxide because it's a 1-to-1 ratio. Everything goes up together. Now remember we said that the rate is also dependent on all kinds of other things, right? It's not like the rate is equal to H2O2. The rate isn't 0.1. You can see here the rate's actually 5. So there's got to be some fudge factor in there. And what is that fudge factor made of? Well, we call it the specific rate constant. It's given the thing K, the letter K. And what it is a constant that encapsulates all those other variables. The temperature, the surface area, what state your stuff is in, what pressure is currently going on, the barometric pressure, all that will have an effect on your rate a little bit. So they can put all those together into a constant, and they just figure that out experimentally. So they say, okay, if the rate was 5, I'm looking at trial 1 here, and I got 5 when I started with 0.10, well, then how do I get K? I divide both sides by 0.1. It turns out, for this reaction, the specific rate constant is 50. And so I could use that. So if I said, hey, what would the rate be if I gave you 1 molar hydrogen peroxide? You could use that K now if you wanted to. Now, actually, let's just go to the next page. I've already got this set up for you. Specific rate constant. There we go. Rate equals K times the concentration by 1. Now this K, this specific rate constant, you have to be very careful with it. It is called the specific rate constant for a reason. It is specific to this exact reaction only. What does this mean? If I change the temperature, I can't use K anymore. I'd have to do another experiment and re-find K. Different day? Well, on a different day, there's a good chance that your barometric pressure has changed. That's just kind of the pressure walking around. Sometimes there's high pressure days, sometimes there's low pressure days. That kind of affects the weather, right? Barometric pressure change, which means new experiment because K changes. K is also dependent on pressure. You get a new jar of H2O2. I guess it would be more of like a bottle. Guess what? K might change. You're not sure if it's got the same impurities. You're not sure if it's got the exact same. Well, this case probably the same surface area because it's a liquid. But you know what I mean. You change the bottle you're using, you might have to re-find your K because that might be in a slightly different crystal structure if you're using a solid. Might be different impurities if you're using a liquid or a gas. You'd probably want to do another reaction and make sure you got the same K. So K is very specific to the reaction you're doing. If you needed to calculate rates for something, you'd basically have to find K first. You'd have to do a mini experiment before you could find your rate constant to use for whatever your real experiment was. So you do have to be very careful with K. It is super specific. I don't know if specific does it enough justice. It's a super specific rate constant. It is only for this exact reaction. So let's look at a quick example of this. I got nitrogen dioxide, which is a gas. Mix it with carbon dioxide, which is a gas. It spits out nitrogen monoxide, which is a gas. And carbon dioxide, also a gas. Cool. So, when I want to find the rate law for this, we would say, okay, well, what's involved in this reaction? My reactants are these two. That's what I'm starting with. That's all I care about. I don't need nitrogen dioxide or carbon dioxide in my rate law because those are products. They haven't been created yet. We are starting. We're going to measure the rate at the beginning of this experiment. Now, there are other ways to measure rate law. Both of them involve calculus and very complicated math. This is by far the easiest way to do it. So this is the only one we're going to look at in grade 12 chemistry. If you really, really get into chem and you're looking into kinetics, like second, third university stuff, after you've done some calculus courses, they might teach you the other methods of doing it. But this is probably the easiest way to do it, honestly. If you have the time and the reactants are available, just run a couple trials, measure your rate. It'd be the easiest way to do it. So what's our rate law? Well, the rate is going to be K times the concentration of NO2 times the concentration of carbon monoxide. But now what we've got to figure out, the important part here, the hard part, is what are our coefficients? I'll call them A and B. Is it first order in nitrogen dioxide and carbon dioxide? Is it second order in one of these? Is it zero order? It can be zero order. It's not common, but sometimes it happens. So here's what we're going to do. We're going to use trial 1 as our baseline here. Why do I pick trial 1? Because it's got 0.1 for both, which is a really easy starting point to compare to. So if I look at trial 2, what have I changed? Well, these stayed the same, which is what I want. I want one thing to stay the same, and I want one thing to change. So in this case, if carbon monoxide stayed the same, I know it's not changing the reaction rate. So my only change in rate here must have come from nitrogen dioxide. And it went from 0.1 to 0.4. So that went up 4 times. What did the actual rate change by? So my concentration changed by 4. How much did this change by? If you need to find out what it changed by, you take what you ended up at and divide it by what you started at. That'll tell you exactly what you changed by every time. So what you ended up at divided by where you started, that tells you how many times it went bigger. So grab the old calculator, 0.005 divided by 0.08. Oh, whoops. I did that absolutely backwards. 0.08 divided by 0.005. There we go. So my initial concentration went up 4 times. My reaction rate went up 16 times. Now, is that 4 to the power 1 or 4 to the power 2? Well, 4 to the power 2, obviously. So we now know that this reaction is second order in nitrogen dioxide. So I'm going to write that down here in my rate law. I've just found out that it is second order in nitrogen dioxide. If I double my nitrogen dioxide, it goes 2 times 2. 2 squared, actually. It goes up 4 times. So it's second order. All right. So that's nitrogen dioxide. Now I'm going to start again. I got to do carbon dioxide. Which trials do nitrogen dioxide stay the same? Trial 1 and trial 3. They haven't changed, so nitrogen dioxide will not affect my reaction rate. Let's take a look at what happens to carbon monoxide. It goes from 0.1 to 0.2, so it goes up times 2. What happens to the reaction rate? Oh, it doesn't change at all. Times 1, there's no difference. If there's no difference at all, it doesn't matter what the concentration of carbon monoxide is. That is what we call 0 order. Because if you think about it, it changed by 2 to the power 0. 2 to the power 0 equals 1. It didn't change. So that's 0th order in carbon monoxide. It's not common. It's actually fairly rare to have something that's 0th order. But that means it doesn't actually matter what your concentration of carbon monoxide is. It won't change its reaction at all. So we got a few questions here. Maybe can I copy these and paste them? Maybe it's a long press or something. Control X? Oh, no, that got rid of one thing. Never mind. We'll just zip back and forth here and figure them out. So, step 1, find K. All right. So, new page. Let's rate out what we know. Our rate law. Rate equals K times nitrogen dioxide squared. And if the other one is to the first power, I don't have to write it at all. Or to the 0th power, sorry. If this is to the 0th power, you can ignore it because it's just times 1. It doesn't matter what CO is. You're timesing it to the power of 0, which means it's going to be 1. So this whole term can be ignored. Anything to the power of 0 is 1. You don't need it. Which makes our rate law actually pretty simple. It's just nitrogen dioxide squared. Now, if I want to find K, I'm going to have to pick a trial to use. And here's the best part. It doesn't matter. Pick any one you want. Usually the one with the simplest numbers, which in this case would be trial 1. But if you do it with trial 2 or trial 3, you'll still get the same answer. So we're going to plug our numbers in. We're going to take our rate, and we're going to put it there. We're going to take our initial concentration, and we're going to put it there. So, I forgot already. What was the rate? 0.005? 0.005 equals K times 0.1 squared. Just want to make sure I got that right. Yeah, 0.1. Perfect. So this is what I got to solve to figure out what K is. So 0.005 equals K times 0.1 squared is 0.01. Divide both sides by 0.01. And I get 0.5 for this reaction. Bonus question. Wait, did I actually ask that question already? I didn't. What are the units of K? What is it? What are the actual units for? Is it moles? Is it molarity? Is it seconds? Is it what? What is K? Now, before we get into this, I want to tell you a little trick. K, being a constant, these usually have units that don't make a ton of sense. So, like, don't be surprised if the units are like, what the heck is that even? It's a rate constant. They're not going to have a physical quantity like moles per liter or moles usually. Usually they don't really represent. So, but let's take a look. I'm going to go back to the beginning here. Rate equals K times concentration of NO2 squared. Okay, let's look at the units we've got. Rate is measured in molarity per second. Cool. K, we don't know yet. This is going to be molarity squared. So I'm just looking at units here. I don't care what the numbers are. Rate is molarity per second. Concentration squared is, well, concentration squared. It's molarity squared. So what do I need for a question mark to turn this into that? Well, I need to get rid of seconds. So I need 1 over seconds. I need seconds on the denominator, because that's how I get seconds at the bottom on the bottom over there. And I need to get rid of one of the m's, right? Because I have 2 m's here. I don't get 1 m on that side. So to get rid of an m, I need to cancel it. I don't like that. It looks weird. SM. Molarity seconds. There you go. So let's try that. If I have 1 over molarity seconds times molarity squared, what happens here? So this is I'm just solving this to make sure I did it right. Well, that molarity cancels one of those. I'm left with 1 big molarity on the top, and my seconds stay on the bottom, which is the same as what we wanted to start with. All right, cool. Which means this is actually the units for our rate constant. It's 0.5 per molarity squared, per moles per liter seconds. Per mole seconds over liter? I don't know. This is what I mean. The actual physical constant doesn't make much sense. Concentration makes sense. It's moles per liter. It's how many moles are in a liter. Rate makes sense. It's concentration per second. It's how much your concentration changes each second. Your rate constant is 1 over molarity times seconds. Doesn't actually make much sense. That's pretty common for rate constants. It's hard to actually wrap your head around what it actually means. Basically, the units are only there to make sure the equation works. So, what was our second question? Let's go back. Second question. If the initial concentration was 0.25, what would the rate be? Well, we have a rate law now, so that should make things easier. Rate equals K times NO2 squared. So we don't know the rate. That's what we're trying to find. Do we know K? Well, we just calculated K. And because this is all part of the same set of trials, K should stay the same. K is 0.5. The question told us the concentration of NO2 was 0.25. Oh, I should have written this outside the brackets. My bad. And of course it is squared because it is second order in NO2. That's what we discovered when we were looking at building the rate law. So we've got everything we need here. It's just kind of a simple matter of plug it in and solve it. 0.5 times 0.25 squared gives me 0.5 times 0.0625. I need half of that. And so my rate is 0.03125. And the units for rate, luckily, always stay the same. It's your concentration change per second. Your moles per liter per second. So that was question 2. Nice. Back here, question 3. What would happen to the rate in trial 1 if we cut the volume of the container in half? Now this seems Kind of random. What do you cut the volume of the container in half? Why does it cut the volume? How's it going to change? Like, volume isn't part of this equation in any way, shape, or form. How could volume change reaction rate? So what you got to think about here with volumes matter. I'm going to write this. This is important. Volumes matter if and only if reactants. That's the worst way I've ever spelled that. Okay, that's bad even for me. Let's rewrite that. Reactants are gases. Like, what? Why would it matter if they're gases? Well, here's the deal. If I take a liter of a gas and then I squish it down to a half a liter, I've got the same amount of gas, just in less container. What I've actually done, I've the same number of moles in less liters, in smaller liters. I've increased the concentration. I've concentrated that gas, right? The more I squish a giant balloon, the more concentrated it gets. So if I cut the volume in half, I double the concentration. So half the volume is twice the concentration. They're an inverse relationship. It's 1 over. So if I cut the volume down by a quarter, it'd be 4 times. If I doubled the volume, I'd have half the concentration. So I've doubled the concentration. What happens if I double my concentration of NO2 and carbon monoxide? Well, carbon monoxide does nothing. Look at our rate law. It doesn't change it. So that doesn't matter. But I've doubled the concentration of NO2. So if concentration of NO2 is times 2, then rate is times 2 squared, because it's second order in NO2. So if I were to actually cut the volume in half but keep the same amount of gas, this rate would go up 4 times. The reaction would happen 4 times faster. So you can see why this would be handy if you were trying to do gas chemistry on an industrial scale. Let's say you were trying to create some kind of like ammonia gas for use in farming. If you know that, oh, I just have to compress things and it increases my rate 4 times, you can create a lot more stuff a lot faster, which is very handy if you're doing stuff industrial and trying to make money off it. Number 4, what happens to the rate in trial 1 if we increased the temperature? Well, remember what we said about the specific rate constant? It's very specific to this reaction. If we increase the temperature, well, K changes. It's going to increase the rate. So in this case, K actually goes up as well. So K goes up. Goes up? That goes up. Then we'll have to go down. No, yeah, if that goes up, rate goes up. That's all I need to know. Yeah, so K changes. K was going to go up. Can I calculate the rate? No. I don't know what the K is. I'd have to redo the entire experiment. All I know is that the rate's going to increase. And we knew this from before, right? If you increase the temperature, you're putting more energy in, you're getting over that activation energy hump more often and more likely, so you're going to have a faster rate of things happening. What that actually translates to in terms of math is we would have to redo the experiment, recalculate K, it would be a bigger number. Because we'd have the same initial here, but we'd have a bigger number there because the reaction rate would increase. That pretty much wraps it up for rate law, though. So if you've got any questions, you know where to find me, and I will see you guys in a little bit.